Hey guys, in this lecture what we're going to be looking at is going to be secants and tangents. So this is pretty much the same as what we did in the previous lecture for sines and cosines, except it's secants and tangents. Now we're not going to go probably into as much detail for these, but you know, it's its own thing and we'll see a little bit of stuff. Now, kind of before we get started here, I just want to remind you of some integrals that you should already know. So here they are. So stuff you know. All right. So first thing is, if you do an integral of tangent x dx, right? What is that? Well, you can get it from the list of common derivatives and integrals, right? But what you do is you write it as like sine x over cosine x, like that. You do a u substitution, which I'm not going to write. And then you would get that is negative natural log absolute value cosine. But we don't like writing it that way. So we write it as natural log absolute value secant x plus c. Okay, and that uses a log rule where you bring the negative up as an exponent and so on. And yeah, okay, so you should know that. I don't know why I wrote out the whole work for it, but you should know that one. Also, you should know the integral for secant squared x dx. Wait, you should, but I want to do this one first. So the integral of secant x dx, we learned it about the same time that we learned the previous one. And I'm not going to show you all the work right here, but it was the natural log of the absolute value of secant x plus tangent x plus c. And it takes some work to get there, but you can get there. Another one you should know, this one is the one you've known the longest. The integral or antiderivative of secant squared dx is just tangent x plus c, because of course the derivative of tangent is secant squared. So we have that. Now another one, which I don't remember if I did this in the lecture on integration by parts or not. It's either in integration by parts or I only did it in my office hours. I feel like I did it twice, but I don't know if I did it twice in office hours for people or if I did it in the lecture as well. But it's a very tricky integral to do, but the integral of secant cubed is 1/2 secant x tangent x plus 1/2 natural log absolute value secant x plus tangent x plus c. Okay, and yeah, so there you go. Now the reason I'm writing these down here is because you want to be able to do these without a bunch of rules. Another thing we could do, I guess, how would you do this? Technically we're going to learn how to do this today, but it doesn't hurt to do this one kind of on its own before we start. So the way you would deal with tangent squared is you would need a trig identity. Now I'm going to write down some trig identities for you today, but you should all know this identity that I'm writing now, right? That's called the Pythagorean identity. Right? If you divide every term here by a cosine squared, then it turns into, right? So if I add this, basically, if I go cosine squared, cosine squared, cosine squared, then it becomes this identity. It becomes sine over cosine is tangent, so you get tangent squared x. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared x. So we get this identity. Of course, you can use it the way it's written right here, but you could also, I guess I'll make this bigger. You could also just rearrange it a little bit, move the 1 to the other side, and you could have tangent squared x is secant squared x minus 1. right? So if you come over here to this integral that I wrote, the antiderivative of tangent squared, you'll realize that you can just rewrite that as the antiderivative of secant squared x minus 1. And then from there, you can just integrate each of these separately, because you know the antiderivative of secant squared is tangent x, and the antiderivative of negative 1 is negative x. So like that. And there you go. So that's some integrals. So we're done with the lecture, right? No, we're at the beginning of the lecture. So you can know all of these before you start. And the one that's really kind of obnoxious is this one, secant cubed. You have to use integration by parts, and then you have to use trig identities like these. And then it's also one of the integration by parts problems where you have to solve for the integral with algebra. So it's a pain, but there you go. So here's some integrals. They're all available on the list of common antiderivatives and derivatives that is posted for you online, but I want them written here so so I can refer to them basically. So I can scroll up, honestly, when I'm doing problems and read the answer rather than have to think myself. Because thinking is hard and I'm not good at it. All right. Let's actually talk about what we want to do then. So just like sines and cosines, the rules for how to integrate this stuff depends on the exact powers you have for the sine and the cosine. So the rules depends on the exact powers. All right, and so specifically, how how are you going to do that? Well, it's different, right? It's different than sines and cosines because we know how to do different integrals, right? The integrals that we know how to do here that are easy, like is number one, this one, the one with the secant squared there, and also one that I'm realizing I didn't write would have also been easy. Let's see, is there anywhere good to put that? Yeah, I want to put this as well. I forgot one. Okay, here's what we're doing. I'm going to cut this, move it down by magic. Then I can come back up here and add one more integral. So one more you should know is this one, right? The integral of secant x tangent x. That's just secant x plus c. I'll put those like that. Okay. So now I think I have all the ones you should know. So back to what we were doing. So just like sines and cosines, the rules depend on the powers of secant and tangent that you have. And so here's an example. So suppose I had this. So here's an easy example. If I had tangent, I'm going to say to the 9th, I'm doing that to illustrate that the power on the tangent doesn't really matter here at all. This would be an easy integral, okay? And it would be an easy integral because all you would have to do is just use a simple substitution, u equals tangent x, because the du would be secant squared x dx, and then you've got your du right here, which is right here, and of course you have your u. I always do that, don't I? Your u is right here, and that's right here. So you go ahead and you substitute that in, and it turns into tangent to the 9th is u to the 9th, and secant squared x dx is just du. That's an easy antiderivative. You just use the power rule, so you go u to the 10 over 10 plus c, and then you substitute in your u, which is tangent. So you have tangent to the 10th x over 10 plus c, and you're done. So that's very straightforward to do. Now, another one that's very straightforward to do is one related to this secant x, tangent x thing. So if I have one set up like this, so if I said, how would I want this? If I said, well, let's just do this. No, that won't work. Let's just do this. If I had secant to the ninth, tangent x, dx. If I had one like this, it's not as obvious as the previous one what to do, because you might be saying, okay, well, I can't just use u as secant because then I have u to the ninth, but tangent x isn't the derivative of the secant, so that doesn't work. Well, it doesn't work unless you do this, right? What you can do is you can take one of those secants off to the side and write it as secant to the eighth x, secant x, tangent x, dx, like so. Because then a u substitution will work perfectly fine, right? You just say, let u equal secant x, du is secant x, tangent x, dx. Like last time, you've got your u, which is right there, and your du you also have because you moved one of the secants over to the side, and now it's separated to make it convenient. So you go ahead and you make that substitution. So you have substitution u to the eighth du, which is u to the ninth over 9 plus c. And u is secant now, so you have secant to the ninth x over 9 plus c. So it was harder than the previous one, but only just barely harder. Okay, and those are relatively easy. Now the thing is that what we want to do is basically for secants and tangents, we want to recognize when we can do it either the way on the left or the way on the right. So we want to recognize that. Recognize when you can use the method on the left and the method on the right. Or on the right. So what do we do? Okay, so let's talk about when we can do the one on the left. So if we want to do the thing on the left, we're going to need a secant squared. If you're going to need a secant squared at the end, what you need to start with is an even power of secants. So our first case here is going to be when you have an even power of secants. So even power of secants and we actually don't care at all about the tangents. Don't care about the tangents at all, really. So that's the first one that we're going to talk about. Even power of secants, and we don't care about the tangents. So what's the method? Well, again, it's easiest to do with an example, so let us do that. So we don't care about the tangent, so let's just have 3 of them just to have some number. Okay? It could have been none, by the way, right? We could have no tangents at all. That would have been fine. So let's say we have 3 tangents, and let's say we have, let's say, 4 secants. Okay? So our goal, if you remember, is that we want to make it look like the integral on the left. That means we want to use a du is secant squared. So because of that, what we want to do is we want to separate off 2 secants off to the side. So step 1, separate secant squared x dx off to the side. That's your first step. So that will look like this. Tangent to the 3x, we're separating this into a 2 and a 2, like that. And our goal is that this is going to be our du later on. It's going to be our du at the end. Now, if that's going to be our du, I shouldn't write that yet though. That's going to be our du. Now, if that's going to be my du, then my u must be a tangent, right? Just like this example over here on the left. If this is our du, then our u must be a tangent. So everything else needs to be tangents. So what you have to do is we have to convert the remaining secants into tangents. How are you going to do that? You're going to use the identity that we wrote. That we used once actually already somehow. But what we want are the identities right here. Right? This right here, this top identity, that's how you change secants into tangents. A secant squared is tangent x plus 1. So we're going to take this one, and that's the one that we're converting. So you simply use, well, what did we say? Secant squared x is tangent squared x plus 1, minus 1. Let's look again. Plus 1. Plus 1. So that's it. You just are going to take this right, did it again. You're going to take this right here, and you are just going to apply this identity, and that's how we're going to get rid of it. So it's going to turn into a integral, a tangent cubed x. The secant squared turns into a tangent squared x plus 1, and then you've got an extra secant squared x dx on the end. All right. From there, what you need to do is you're going to need your substitution. So now you do your substitution. So we're going to let u equal tangent x. Du is going to be secant squared x dx. So we've got our tangent. Did it again. Getting worse at this. We have u equals tangent x. So here's a tangent. Here's a tangent. And then we've got our du is secant squared x dx, and it's right there. So we're going to make those substitutions. We're going to have the integral tangent cubed is going to be u cubed. Tangent squared x plus 1 is going to be u squared plus 1. And then our secant squared x dx at the end is simply going to be du. So there we go. Now all we got to do is integrate. But we should simplify it first a little bit, and then we can integrate it. So how do we do that? Well, we should multiply this out. We should multiply the u cubed in. So when you do the u cubed times u squared, I guess I'll actually write that on here. So let me get a different color. You're going to distribute the u cubed like that. So you're going to end up with u to the 5 plus u to the 3 du. So that's how you simplify it. Then you're going to find your antiderivatives. So the antiderivative of u to the 5th is going to be u to the 6 over 6. And u cubed is going to go to u to the 4th over 4. And then plus c. So there we go. Now your last bit doesn't even really need to be numbered here, but you're going to substitute back to the original variable. So substitute back to x. In this case, it's an x. So u was what? Tangent x. So you're going to have tangent to the 6 x over 6 plus tangent to the fourth x over 4 plus a constant. Okay, so that was our first example here. I'm going to go to the homework real quick just to see what kind of nonsense they make you do on this. Okay, that's very easy. First problem was easy. That's nice. Second problem was what? Oh, okay, that's fine. All right. Yeah, that's not so bad. Not so bad. Okay. So, yeah. All right. Just about done here. And then, okay, yeah, let's just, okay, forget this. This is taking too long. Let's just go ahead and do one. So, so that's what we did there. Now, of course, just like on all of these, you can make your life a little bit harder. I mean, not that you should, by having higher powers of stuff here. So like if I had something like this, so like I said that this method was for if we had even power of secants. So if I had one like this, let's say, let's do two things different. Number one, let's have a higher power. So let's say secant to the 8th. I think I'm going to regret this. Yeah, I'm probably going to regret this. I'm trying to think here. Let's say I have secant to the 8th x dx. Oh, and then I said two things. So I'm going to change that x to, let's say, 3y. Then I need a dy. Okay, so let's say we have to do this. Hopefully this won't turn terrible, like many of my made-up examples do. What would we do here? So we're going to start off the same way. So we're going to try to save two secants off to the side. So we go secant to the 6th, 3y, secant squared, 3y, dy. Now, of course, this is no good, right? Because it's a secant to the 6th. We need everything to be in terms of tangents, except for that secant, except for this. This is fine, but we need everything else to be in terms of tangent. So we need to use the identity to turn secants into tangent. Well, in order to do that, we need to see the secant squared. So you have to write secant to the 6th as secant squared to the 3. Secant squared 3y dy. Okay, so when you're there, now you need to do what? Well, now you use your identity. So our identity is the same. Where's the identity? I'm scrolling up for it. So here's the identity. Secant squared is tangent squared plus 1. So you rewrite this as tangent squared 3y plus 1 cubed. Secant squared 3y dy. Now this is actually fine. The main problem here is, you'll see momentarily. So we're going to do our substitution, right? You do your substitution before you start multiplying stuff out, if you can. So let u equal tangent 3y. So du is going to be 3 secant squared 3y dy. Divide both sides by 3, you get du over 3 equals secant squared 3y dy. And we should be able to make this substitution because we have this right here for our secant squared 3y dy. And then I've got my u is tangent 3y, and we just have tangent right there. So that should be easy to make the substitution. So make the substitution. you've got u squared plus 1 cubed, and then you've got du over 3. You can take the over 3 out in front, but you still have u squared plus 1 cubed du. Now this right here, the u squared plus 1 cubed, you can multiply out by hand. Generally what I would do, like if I was doing this like to show somebody later, I would not multiply that out by hand probably. Well, it's cubed, so I might do it by hand. But if it was a 4th power or something, what I would definitely do is I would just remember it, u squared plus 1 cubed, and I would head over to Wolfram Alpha. So I wouldn't use Wolfram Alpha for the whole integral, but I would use it for this. I would say just u squared plus 1 parentheses cubed. And if I scroll down a little bit, it should tell me what I get when you multiply this all out. There it is. So it's just u to the 6th, so, and then 3u to the 4th, 3u squared plus 1. So u to the 6th, I'm never going to remember that. Integral 1/3 u to the 6th plus 3u to the 4th plus 3u squared plus 1 du. Did I get that right? I have no idea. Let's see. That's not right. Oh, there it is. U to the 6th, 3u to the 4th, 3u squared plus 1. That's right, right? That's right. I think that's right. I'm going to pretend it's right. Okay, so once it's multiplied out, then you can just do the integral. So this wasn't really that much extra work to do it this way. So you just have u to the 7 over 7, u to the 5th over 5, u cubed over 3, and then a u plus c. And from there, you just substitute in what your u is, which is a tangent somewhere, tangent 3y. So tangent to the 7th, 3y over 7. 3 tangent to the 5th, 3y over 5. 3 tangent cubed, 3y over 3, plus tangent 3y plus c. And there you go. And that's it. That's how that would go. So why did I do that one? I had no idea. No, the reason I did that one was because I wanted you to see what happens when you have a little bit higher power there that you have to deal with. I mean, I guess, sorry, right there is where the power was higher. 8th power. So yeah, so you end up at some point having to multiply some stuff out. And when you do, like when you have to work this out, I mean, use a computer, right? Why not? Right? There are not a lot of advantages to, having to do this class as an online class compared to in-person class. But one of them is that you're probably sitting at a computer, and so go ahead and use it for stuff like that. That's what these tools are for, right? You don't want to use a computer to solve all the problems that you have, because then you're going to get to the point where you're not going to know, like you're going to have a problem and you're not even going to know how to get started with it. So you can't ask the computer to do anything because you don't know what you need done. So you want to understand it as thoroughly as possible, but you want to use a computer just to save you time. Like I could multiply that out. Like I know that this right here is something that can be multiplied out, right? And a computer is good at that. So have the computer multiply it out. I'm not doing it because I'm not smart enough to multiply out u squared plus 1 cubed. I'm doing it because I'm too lazy to multiply out u squared plus 1 cubed. And that's fine, right? I hope it's fine. I think it's fine. Okay to be lazy. I'm the laziest human being in the world. Okay. What are we doing now? Okay, so that was those. That was the first kind, right? So we basically just talked about like all the integrals on the left here. when the power on secant was even. Now, the case on the right here is a little bit harder to describe. So you have to think about what you need here. Let me just go on my computer. Make sure OBS is still running. I film these videos like I'm a Twitch streamer. So like we're gonna do this and then we're gonna play, you know, a speed run of Super Mario World or something. Yeah, I'm a retro video game streamer. You don't know that. I wear a wig, so you can't recognize me. All right, so what are we gonna do here for this integral? So what you need in order to get this kind of thing to happen is, well, first of all, obviously you need a secant and a tangent, right? Because it's secant tangent. And also what you need is secant to, like you see that secant to the 8th, everything needs to be secants. So everything needs to be secants. You're not allowed to have tangents except for this one tangent, okay? Now, in order to get it down to one single tangent, you need to start with an odd number of tangents. So you have to start with an odd number of tangents in order to get the tangent part of that. But you also need to have at least one secant, because if you don't have a secant, then how are you going to get that secant right there? Okay. Now, even if you don't, 100% remember what I just said, or because I was babbling, that's fine. I'm just going to write the rule down, and then you can just believe me that it makes some kind of sense. Okay, so here's the next case. Okay, so the next thing we're going to learn is when you have an odd power of tangent and at least one secant. That's what you're going to need. If you have that, then you are going to be able to do what we're about to do, which is this. So let's see an example. I guess I'll write it in red. No, let's switch to a different color. Let's go pink. Okay, so you have an odd power of tangent and at least one secant. So here is an example. We need, well, what I just said, right? So I'm going to need odd powers of tangent. So let's just say tangent to the 5th x, and we need at least one secant. It actually does not matter how many secants we have otherwise. So let's just say it's secant to the 5th. Okay, so tangent to the 5th, secant to the 5th, x dx. That meets the requirements. Okay, now our first step is we want to save off the thing for the du, just like we've done a million times now. So we're going to save in this case, a secant x, tangent x dx off to the side. All right, so let's do that. So we're going to have tangent to the 4th x, secant to the 4th x, put those in parentheses, and then a secant x, tangent x, dx. And we're saving this to be my du later on. Now, after we do that, that's the du for secant. That means everything needs to be a secant. So if everything needs to be a secant, then we can't have this. We need only secants. So you need to convert all other tangents into secants using the identity. What identity? The same one that we've been using. So the other identity, not the other identity, the identity box. All right, so save a secant, convert the other tangents into secants. So let's do that. So if we're converting these other tangents into secants, then I'm going to do that trick that I did before, where tangent to the 4th is going to need to be written as tangent squared secant to the fourth x, secant x, tangent x, dx. Now, where's the identity? The identity we need converts tangents to secants. So we want this form of that identity. So tangent squared is secant squared minus 1. Secant squared minus 1. So that tangent squared x equals secant squared x minus 1. So you put that in for the tangent. Secant squared x minus 1 squared, secant to the fourth x, secant x, tangent x, dx. So this is saved off to be your du. The secant to the fourth is already done, so we're ready to do our substitution now. So our substitution is going to be what? Use u equals secant x. Du is going to be secant x tangent x dx. So we've got this already set up, and then we have our u, and there's a secant and there's a secant for my u's. So let's use this not identity. Let's use our substitution. So we have the integral of secant squared minus 1. Secant is u, so that's u squared minus 1 squared, and then u to the fourth, and then du. Right? So these are, hopefully by this time, all of these kind of problems are starting just to look the same to you. And that's really good if they are, because, you know, they are all the same. So they shouldn't look different just because they are slightly different. They should look the same because they're all largely the same. So what do we need to do? We need to simplify and then integrate. Whoa, weird box. All right, so what do we need to do to simplify? Well, really, it's just this right here needs to be all multiplied out. And again, you can obviously do that by hand, or it's another, save some time using Wolfram Alpha if you want. So it's u squared minus 1 squared, and then u to the fourth. So you come up here, it's u squared minus 1, was it squared? Squared? And then we had another u to the fourth. So I don't know if it'll understand this correctly. Let's see. Yeah. Is that right? U squared minus 1 squared u to the fourth? And if it is, it's u to the 8th minus 2u to the 6th plus u to the fourth. So 1 minus 2, 1, and 8, 6, 4. So I think it is, that's an integral symbol. What was it? U to the 8th plus or minus 2u to the 6th plus u to the 4th. I don't know why I did Wolfram Alpha. We could have easily done this. All right. So there's your integral. So we integrate. So power rule again, u to the 9th over 9 minus 2u to the 7th over 7 plus u to the 5th over 5 plus c. How are we going to finish this up? Probably we're just going to substitute back to the original variable. So substitute back to, in this case, x, I think. All right, so what are we going to get? Just, actually, I don't know. What was the substitution? Secant. So it's secant to the 9th x over 9 minus 2 secant to the 7th x over 7 plus secant to the 5th x over 5 plus c. And that's my answer right there. Should label that in case somebody's coming along later. That's the answer. All right. So, yeah. So not much different than the other kind. Yeah, not much different than the other kind. All right. So there's basically one other thing here that I would like to mention. And so the other thing that I would like to mention is reduction formulas. And a lot of times I would not have taught this in this class, but Newton Alta does, and I don't get to control too closely what the formulas are. So we're doing reduction formulas because they want to, so we will. All right, reduction formulas. What are they? So the idea is this. We know some advanced techniques for integrals now. Well, basically we know integration by parts, but that's an advanced technique. The problem with integration by parts is that it can take a long time, right? And so we don't want to necessarily have to do integration by parts every time we have an integration by parts integral. So we want to avoid it. And so the way to avoid it is you let somebody else do integration by parts for you, right? That's good. We always like to cheat. And then we just write down what the result was, okay? That's what a reduction formula does. So like here they are. So there's one for tangent and one for secant. So here's the one for secant. Secant to the n x dx equals 1 over n minus 1 secant to the n minus 2 tangent x plus n minus 2 n minus 1 integral secant n minus 2 x dx. Looks like a mess, right? Sure it does. Here's another one. Here's the one for tangent. So it is 1 over n minus 1 tangent n minus 1 x minus the integral tangent n minus 2 x dx. All right. Now, if, hopefully I wrote these right. If I didn't and I screwed them up and you need the correct ones, you need to look at the textbook, right? So if you look in, oh gosh, what's the section number? I don't remember the section number, but if you look in the trig integral section on secants and tangents, of course, in OpenStax Volume 2, that's the one you want. OpenStax Calculus Volume 2. You can definitely find those formulas. And, I had to look them up because, like I said, I don't normally teach this. So let's see what they can do for you. Like, why do we care, right? These are big, messy formulas. Why do we want them? So the reason you want them is because you would be able to do integrals that you would not otherwise be able to do. Like, for example, I told you that this integral was hard. Right? I told you that this integral was hard, and it is. In fact, though, I see that the homework wants me to do this one. I'm going to do this one. It doesn't matter which one I apply it to. But, oh, actually, can I? Hold on. No, because I would have to use a U substitution. I don't want to use a U substitution. I'm going to go back to the other one. Sorry. Let's say I have this. So the idea is this. So you're matching up the power here. You say, okay, there's a third power, and in the formula for secant, that's called n, right? So you identify that n. So we see n equals 3, right? So all you're going to do then is you're going to write out the entire formula over here on the right, and you're just going to fill in a 3 for every n. That's all. It's not that hard. I mean, it's a lot of kind of writing, but no thinking. A lot of writing, no thinking. Okay, so 1 over 3 minus 1. Then you have secant n minus 2, so that's 3 minus 2, x, tangent x, plus, then you have n minus 2 on top, so that's 3 minus 2, over n minus 1, so that's 3 minus 1, integral, secant 3 minus 2x dx. Okay, so work out all those minuses, basically. So 1 over 3 minus 1 is 1/2. And then secant 3 minus 2 is just secant to the 1 x tangent x. And then you have 3 minus 2, which is 1, over 3 minus 1, which is 2. And then integral secant to the 1 x dx. Well, if you didn't know the integral of secant cubed, look at what we did. What you did was you changed the secant to the cubed into an integral of just a secant, right? So basically what happened was the power dropped by 2. It went from 3 to 1, so it dropped by 2. And that's why it's called a reduction formula, because it results in a lower power of the secant. And hopefully the lower power is one you know how to integrate, which it is, because before today you should have known that the antiderivative of secant x was natural log absolute value secant x plus tangent x, and then just add a plus c. And so what I just did there, I just derived a formula for, I'm going to leave it an oval. I don't know why. We just derived a formula for the integral of secant cubed, right? So if I scroll up here, all the way to the top here, if you didn't believe me about this formula right here, well, now you should, because we just came up with it, okay, using that reduction formula. Now, one thing I want to mention too is how many lines of work did that take me? This took me basically 3 lines of work, right? It took me 3 lines of work, and I could have probably done it in 2, because I might have been able to start with this line, the second line, if I can do 3 minus 1 and 3 minus 2 in my head, which is, you know, not 100% sure, but sometimes I can do that. And then I would get this for my answer. Now, anyway, point is 3 lines of work. What would it have taken without that method? Without this method, I think that on an entire sheet of paper, maybe I could have solved it on one full sheet of paper. Okay, maybe. It's a long problem, okay? And like I said, it's integration by parts, and it involves trig identities, and it's one of the integration by parts problems that involves solving for the integral algebraically rather than just finishing the problem. Pretty tedious, but the power reduction formula really just made it easy. Okay. All right, let me think. One thing I do want to mention, because I do see it in the homework, is if you want to use the reduction formulas, you do have to make sure it matches pretty much exactly. So like on the x there's no 2x or 3x or 4x or anything, right? It's just x. And so if you have a coefficient, you have to do the u sub first. So let me just do an example of that real quick. So like, let's say I have tangent to the 3 of, and I'm just going to say like 5x dx, right? And so you have tangent to the 3, 5x dx, and you want to use this formula, obviously, right? Because you got a formula for it. Well, you can't because it's an x and you have a 5x. So before the power reduction, before reduction formula, you need to do a u sub. Do a u sub, or the constant will be wrong. Okay, so you have to do this u sub. So you just say, it's not hard, right? You just say let u equal 5x. It's just the 5 that's the problem. And then du is 5 dx, or dx is du over 5. So it's a pretty simple one. You got u equals 5x, so there it is. And then you've got dx is du over 5, so there it is. So you make your substitution. You've got tangent cubed u, and then dx is du over 5, so I just go 1/5 du like that. Okay, so at this point now you can do the reduction formula because you don't have a constant there. Okay, now you can do the reduction formula. All right, so what will that look like? Well, you've got the 1/5 out front. So basically you just, I don't want pink, I was writing in red. 1/5, and then you do the whole reduction formula inside of that, because we have the integral tangent cubed. So you go to your reduction formula, what do we got? What's n, by the way, right? We have another n cubed, don't we? N equals 3, sorry, not n cubed. So we got another n equals 3. So what do we have? We have 1 over n minus 1. So 1 over 3 minus 1, tangent, what is it? Tangent, what am I looking at? I'm confused. Oh, there it is. Tangent n minus 1, so that's tangent 3 minus 1, x, except it's not x, it's u. Then we have minus, okay, minus integral. And the integral is tangent n minus 2. Tangent n minus 2, which is actually 3 minus 2, I should write. 3 minus 2, u. Keep scrolling up too far and then getting confused. All right. So hopefully I did that right now. So then what you have is, so you got your 1/5 parentheses, 1/2 tangent squared u minus the integral of tangent 3 minus 2 is 1, so just tangent u du. Well, I'm not going to change anything back to x yet. We need to integrate tangent u du. Well, we have that written down somewhere near the top. The integral of tangent x dx is ln absolute value secant x. We have ln absolute value secant x plus c. Oops, I did it again. Secant u. All right. At this point, you can substitute in what u was. U was 5x. So you end up with 1/5 parentheses 1. That says 1/2, and I wrote ln 1/2 tangent 5x, tangent squared 5x, minus ln absolute value secant 5x plus c. And if you want, you can multiply that 1/5 through, or you can be lazy like me and not. And there you go. So that's my answer there. What's the point? Again, so the point is the reduction formulas can save you a lot of work, first of all. And also, if you want to use a reduction formula, you need to do whatever u substitution you have to first, so that there's not a constant on your variable like there was on this tangent cube 5x. Okay. And all right, I think that's it. Was this a long video or a short video? Let's see. Oh, 55. pretty long. Okay, so that's it for this video. Good luck. This homework's a lot easier, I think, than the sine and cosine homework somehow. All right, see you next time.